Bismillahirrahmanirrahim. This is our week number 6 and lecture number 6. So the first topic is critical depth in non-rectangular channels. Okay, I think the topic of the title of this topic should be very generalized. It should be critical depth in all kinds of channels. Okay, we developed the relationship of the critical depth for rectangular channels only in one of our previous discussions, but now in this class we are going to develop the critical depth for the critical depth which you can use for any kind of channel. We are going to develop the relationships which you can use for example, trapezoidal channel, triangular channel, circular channel, or even you can use these relationships for the rectangular channel also. Okay, these are the generalized equations which can be used for any shape, for any cross section of the channel. So let's take a start. Here you can see that we have an irregular channel for which this is the level of water and T is the top width of the flow. For the analysis of the flow in this channel, I have taken a horizontal differential strip. You can see this is the horizontal differential strip and the depth of this strip is dy. So what will be the area of this strip? Its area will be its width into depth, that is T into dy. This will be the area of the strip which we will use in this equation for the analysis of this irregular channel. So taking start with the equation of the well-known specific energy head equation, that is E is equal to y plus square of V divided by 2G. And we know that this V is equal to discharge per unit area of the flow. So putting the value in this equation, we get E is equal to y plus square of Q divided by 2G into square of A. This is equation number 1. Since we want to do analysis for the critical flow, therefore I will take the derivative of this equation number 1 and I will make it equal to 0, because this is the mathematical rule to find the value of maxima and minimum. Since I am going to find the value for the critical flow, and we know that critical flow is the flow where specific energy is minimum for a constant discharge, for a given discharge. So for the minimum value of specific energy, I will take the derivative of equation 1 and I will make it equal to 0. Okay, you can see here I have taken the derivative of this equation number 1 and I have make it equal to 0. Here you can see in the derivative I have got this term dA by dy, and we know that the area of the differential strip, as I already told you, is T into dy, that is its width into its depth. Okay, or or its length into its width. So this is dA is equal to T into dy. So dA by dy is equal to the top width, and here I have written C as a subscript. I have denoted it as a critical top width of the flow, because I have taken the minimum value of the specific energy. I have taken the derivative equal to 0. So all the terms have been turned into the critical terms. This is the critical discharge, this is the critical area of the flow, and this is the critical top width of the flow. By simplifying this equation, we get this term Q square of Q divided by G is equal to cube of the area of the flow and divided by the critical top width of the flow. Now once again I want to recall that this is a general equation for critical flow in a channel. You can use this equation for even rectangular channels also. Okay, if you are going to use this equation for the rectangular channel, then here for the area of the flow you have to put the value of the area of the flow in a rectangular channel. That is very simple, B into Y. width of the flow into depth of the flow. If you are going to use this equation for the trapezoidal channel, then here for the area you have to put the value of the area of a trapezoid. If you are going to use it for a circular channel, then you have to put here the value of the area of a circle. Okay. So it depends upon the situation and the numerical problem you get. You can modify this equation according to your need. Okay, from this equation number 2, we can further simplify the equation, and we have got this term equal to square of VC by G is equal to AC by TC, and we know that this AC by TC, that is area of the flow divided by top width of the flow, this is equal to the hydraulic depth. Okay, remember that hydraulic depth is known as the area of the flow divided by top width of the flow. This is known as the hydraulic depth. Okay, and you can see that I have further simplified the equation. V square C divided by G into YH is equal to 1, or if you take the under root of this whole equation or both sides, we get this term VC divided by G into YH is equal to 1. This is known as the Froude number. Here we can see that Froude number is equal to 1 for the critical flow. In case of the rectangular channel, we developed the equation for the Froude number as BC divided by G into YC. Here it was the depth of the flow only, but here in this equation it is the hydraulic depth. So once again I want to tell you that this is the generalized form of the equation, and you can modify it for any kind of channel. Let's suppose I have modified this equation for the rectangular channel. Here you can see that what is hydraulic depth? Hydraulic depth is equal to area of the flow divided by top width of the flow. And we know that in case of the open channel, area of the flow is equal to B into Y, and top width of the flow is equal to B. Both the B's will be cancelled with each other, and we will get that hydraulic depth is equal to the depth of the flow. So putting the value of YH is equal to YC in this equation, and you will get this term VC divided by under root of GYC is equal to 1. This is the equation which we developed for the rectangular channel in one of our previous discussions. That was this equation you can use only for the rectangular channels, remember, and for all other types of channels you can use this equation. Students often mistake here. We ask them to find the Froude number for the triangular or any other kind of channel, and they mistakenly use this equation, which gets wrong. So be careful about using the equation and make these concepts clear. Okay, if we divide equation number 2, both sides of equation number 2 by 2, then what will you get? You will get this equation number 3, and if you put this equation number 3 in equation number 1, then you will get this term, that is minimum specific energy is equal to YC plus AC divided by 2 into TC. AC is the critical area of the flow and TC is the critical top width of the flow. So this is the equation for minimum specific energy. If you remember that for rectangular channels we developed an equation that's minimum specific energy is equal to 3 by 2 into critical depth of the flow. So but here the equation looks different. If you modify this equation for the rectangular channel, if you put here the value of the area of the rectangle, and if you put here the top width of the rectangular channel, that will be equal to B, you will get to know that the equation becomes E minimum is equal to 3 by 2 into critical depth of the flow. So this was the generalized form of equations which you can use for any kind of channel for the critical condition only. Okay, this is our next topic, that is occurrence of the critical depth. We are always interested in finding the occurrence of the critical depth in a channel. It is very important for the analysis of all kinds of channels. and it is also very important for the designing of the artificial channels. So there are many uses of the critical depth. One of the use we can discuss here is this. Let's suppose there is sedimentation in a channel and you want to cope with this situation. So first of all, in order to cope with the situation of the sedimentation, you have to find the state of the flow in a channel. Why? Because subcritical flow and supercritical flow behave differently for the sedimentation. We know that for subcritical flow, the depth of the flow is higher and its velocity is low. In other words, you can say that for subcritical flow, its potential energy is higher than its kinetic energy. And what happens, since the velocity is low, the settlement of the sediment particle is very high. And this is what we see especially in the reservoirs. The reservoirs, especially behind the dam, have the same problem. When the water is stored in a reservoir behind the dam, what happens? The water, the approaching velocity is zero, or you can say that the function of the reservoir behind the dam is the storage of water. Since there is no velocity, so what happens? The sediment particles get settled down at the bottom of the channel. While in case of the supercritical flow, we know that the velocity is higher as compared to the depth of the velocity is higher and depth of the flow is small. In other words, you can say that kinetic energy of the flow is higher and its potential energy is low. So greater the kinetic energy, or you can say greater the velocity, greater will be the erosion of the beds and the banks, and there will be high siltation, means the particles will move fastly with the water, as and there will be less settlement of the particles. So when you cope with the situation of, when you want to cope with the situation of the sediment, you must know that what is the extent of the sediment particles, how they are getting settled, how they are getting eroded. And for that, you must know about the state of the flow, whether it is subcritical state or it is supercritical state. So if you know about what is the critical depth and what is the subcritical and supercritical state of the flow, then you can cope with this situation. So here is the next topic, that is occurrence of the critical depth. We have six situations where we can have the critical depth of the flow in a channel. We are going to discuss these cases one by one. Case number one is when flow changes from subcritical to the supercritical state. Case number two, when flow changes from supercritical to the subcritical state. Case number three, when a channel having mild slope ends at free outfall. Number four, when water from a reservoir enters a canal having steep slope. Number five, if the channel bottom is humped. And number six, if the side walls of a channel are moved in to form a contracted section. So we are going to discuss these topics one by one. Number one is when flow changes from subcritical to the supercritical state. Here you can see that this is figure number one, where we have a mild slope and it is connected to the steep slope. Okay, so what will happen? We know that there is a subcritical flow on a mild slope. This is a mild slope and the depth of the flow is higher here. And when water goes to the steep slope, you can see this solid line. This is the flow of water. You can see now this is the depth of the flow, y02. Here y01 is the depth of the flow, and here y02 is the depth of the flow. So this is the subcritical state and this is the supercritical state. And how we comes to know? Remember, when the mild slope changes into the steep slope, then we have the critical depth of the flow at this situation. Here you can see that we have the critical depth of the flow, and if you extend a dotted line from here, you can see that this is the critical depth of the flow, which is smaller than the normal depth of the flow. And if you extend the dotted line from here, you can see that the critical depth of the flow is greater than the normal depth of the flow. Okay, the critical depth of the flow is written here, and here I will suggest if you write it here, it will be much clear that this is a section of the channel where the critical depth actually exists. Okay, you can see that this NDL, this is the normal depth line, shows you that this is the actual uh, flow on the mild slope. This is the actual depth of the line where you have this depth of the flow, that is y naught 1. And here also this solid line is normal depth line, while this dotted line is denoted by CDL, that is critical depth line. It shows you that this is the line where we can have the critical depth of the flow. So if you draw these dotted lines, that is critical depth of the flow, at the upstream side and at the downstream side, it will be much clear that where the flow is subcritical and where the flow is supercritical. Here you can see that the depth of flow is greater than YC, so we have a subcritical flow, and here the depth of flow is smaller than YC, so here we have a supercritical flow. Okay, forget about these S2 and M2 at these situations. These are the names of the curves which we will discuss after midterm exam. So no need to think about these two things, M2 and S2. And even don't write about these if you are going to discuss, let's suppose if you get a question to find to draw these slopes or to find where the critical depth occurs. If you draw this figure for any kind of situation, there's no need to write M2 and S2 because you don't know about these things right now. Okay, this is our case number 2, where you can see what's the title of this case: when flow changes from supercritical to the subcritical state. Okay, always remember, whenever the flow passes through the critical depth of the flow, it always changes its state. The subcritical will change into supercritical, and supercritical will change into the subcritical state. Okay, this must be remembered, that the state of the flow changes when it passes through the critical depth of the flow. Here you can see in figure number 2 that we have a steep slope which is converted into the mild slope. Okay, this is the point where the two slopes are connected. You can see that this is the normal depth line. This solid line is the normal depth line, means this is the actual depth of the flow. You can see here that this is y01. And what will happen when the flow will comes to the steep when from the steep slope the flow will comes to the mild slope, there will be a hydraulic jump, and after hydraulic jump the depth of the flow will be increased. Why? Because this is a mild slope. The flow of very high velocity, here at the steep slope the velocity is very high, and when it comes to the mild slope the velocity get an abrupt change. The velocity will be stopped. Its kinetic energy will be converted into the potential energy, so a hydraulic jump will be created. And this is very, very obvious. It looks like, for example, a high velocity flow is coming and you give it a sudden break. So what will happen at the sudden break? The depth of the flow will be increased, but before that there will be a disturbance, a kind of disturbance that is known as the hydraulic jump. So hydraulic jump will be created, and then the depth of the flow will be increased. Here you can see that now the depth of the flow is y02. At section 2.2, the depth of the flow is y02. In between hydraulic jump, we get the critical depth of the flow. So remember, whenever there is a hydraulic jump, then the critical depth occurs somewhere in between the hydraulic jump. You can see again that this is the situation where we have the critical depth of the flow, and from this critical depth of the flow, if we extend a dotted line that is known as the critical depth line on both sides, you will come to know that here the critical depth of the flow is greater than the normal depth of the flow, and here the critical depth of the flow is smaller than the normal depth of the flow. So here we have the supercritical state, and here we have the subcritical state. This is case number 3, when a channel having mild slope ends at free outfall. You can see that this is a channel having mild slope. The water is coming towards the end, and here we have a free outfall. What is a free outfall? In our common language, we know it as an upshar. ठीक है, जो upshar होती है, that is known as a outfall, free outfall. Here we have a free outfall, and you can see that since this is a mild slope, here the depth of the flow is y0. It will be obviously a subcritical flow, and exactly at the outfall, the depth of the flow is known as the brink depth, and it has been observed that the critical depth will exist, and it will be at a distance of this term, yb is equal to 3 to 4 times yc. So if you calculate here the value of the yb, if you measure what is the value of the depth of the flow exactly at the end, then you can find the value of yc, that where the yc will exist. Okay, yc will exist at this particular distance, which is equal to yb is equal to 3 to 4 times of yc. So this is the situation where we have the critical depth. And once again, if you extend a dotted line from the critical depth of the flow, you will come to know that this actual depth of the flow is higher than the critical depth of the flow, and thus it is the subcritical state. Sorry. Okay, case number 4, when water from a reservoir enters a canal having steep slope. I have taken this figure from your Franzini book. You can see that here we have a reservoir. This is the depth of the flow in a reservoir, and from the reservoir the flow is entering a channel having steep slope. Here we have a steep slope, and you can see that when water will enter from the reservoir in a steep slope, exactly at the entrance we will get the critical depth of the flow. And now you can see, if you extend the dotted line from here towards the upstream and towards the downstream side, you will be able to know that here we have a subcritical state of the flow, and here we have the supercritical state of the flow. Okay, case number 5, if the channel bottom is humped. Humped means that if the channel bottom is raised. How it can be raised? You can raise the bottom of the channel by construction of a weir. Here you can see that this is the side view of a channel. This is the bottom of the channel, and this is the weir over the channel. You can see that P is the height of the weir. You can see this is the height of the weir, and H1 is the depth of the flow from this point up to this point. This is the depth of the flow. You can see that this is the level of water, so this is the depth of the flow, and this is the energy line. So this is the total head of the flow, that is potential energy plus kinetic energy at the upstream side. And what will happen when water will flow from channel over the weir, then the critical depth of the flow will occur here in case of the weir. In case of weir, we can have, or we may have, or we may not have the critical depth of the flow. It all depends upon the design of the weir, how you are going to design the weir. If the hump is designed in such a way to have the critical depth, then it will give you the critical depth. Otherwise, it will not give you the critical depth of the flow. So always remember, whenever there is a weir, You must not think about that here we have a weir, so the flow, the depth of the flow will be definitely the critical depth of the flow. It all depends upon the design, and we will inshallah discuss it in our next class also, that what should be the height of the weir in order to have the critical depth of the flow over the weir. But remember that whenever the weirs are constructed, uh, usually the height of the weirs are taken in such a way to have the critical depth of flow over the weir, because we know that where we have the critical depth of the flow, that becomes a control section. Control section means a section where you can find the relationship between the depth of the flow and the discharge. You can easily find the depth of the flow over weir. We have very simple equations of the weir. You have already discussed these equations in your fluid mechanics 1 course, and we will also develop the equation in our next class. We have very simple relationships, we have very simple equations for the weir. With the help of that equations, we can easily find the discharge over the weir. And we know that the discharge over the weir is equal to discharge in a channel at the upstream side. So this is known as the control section. Why? Because once you know the depth of the flow over weir, you can easily find the discharge in a channel. So normally the humps or the weirs are designed in such a way to have the critical depth over the weir. This is the last case. If the side walls of a channel are moved in to form a contracted section. Here you can see in this image that we have an open channel, and this section of the open channel is contracted. You can see that here we have a kind of construction with the help of which we have reduced the width of the channel. The water will flow through this contracted section and its discharge will get higher. Okay, area kam hoga, when the area will get smaller, the velocity will get higher and the discharge will get higher. So this is known as the contracted section of a channel, and in this contracted section of a channel you can have the critical depth of the flow. Again, it depends upon the design of this contraction. What is the value of the contraction of this channel? You can have or you cannot have the critical depth of the flow in this channel. But again, normally the contracted sections are designed in such a way to have the critical flow and to have a critical depth in this section. Here you can see that this is the top view of the channel. This is the normal width of the channel, and this is the contracted section of the channel where the width of the channel is b, small b. The original or the actual value of the width of the channel is capital B. The water is going here in a channel. The water is flowing in a channel, and when it will flow through the contracted section, the discharge will get higher. The concept is similar to that of the pipe. We know that smaller the dia of the pipe, higher will be the velocity, and greater the dia of the pipe, smaller will be the velocity. So this is the same concept. When you will get the small area, then the velocity or the discharge will get higher. Okay, here you can see this is the top. This is the top view of the channel, and this is the side view of the channel. Here in the channel we have this much total depth of the flow, that is h1, and here in a contracted section we can have the critical depth of the flow yc, and if not, then we have the simple depth of the flow, that is h2 or y2. So these are the 6 simple cases where we can have the critical depth in a channel. Remember that the first 4 cases are the obvious situations for the occurrence of the critical depth, and the last 2 cases depend upon the design of the engineer, that how the weir is designed and how the contracted sections are designed, and it all depends upon the design whether we have a critical depth of flow in these situations or we don't have any critical depth. Boys, are you present here?
Yes, ma'am.
Okay, that's good. अच्छा जी, इसके बाद we have a last topic of the transitions in the channel. This is a figure from your Franzini book, so we will take a start from this. Okay, we can have two types of transitions in a, we can have number of transitions in a channel, in fact, but we are going to discuss only two simple cases. We are not going to discuss the complicated cases that is beyond the limit of our course. We are going to discuss only two types of transitions, that what will happen when we have a hump on a channel, that is wear on a channel, and what will be happen if we have a contracted section in a channel. So we are going to discuss these two kinds of transitions in a channel. This is from your Franzini book. You can see here that this is a mild slope, and here we have a hump. The height of the hump is P. So what will happen? Water flowing from the channel, when it will approach the weir, there will be a small depression in the flow, and again it will come back to its original state. Okay, when you will increase the height of the hump, you will see that the depth of the flow is further reduced on the depth of on the weir. You can see that here the depth of the flow is decreased on the weir. Here the depth of the flow is further decreased on the weir, but once it goes from the weir, it again gain its total energy, and has the same depth of the flow as it was at the upstream side. You can see that in both these cases, the depth of the flow at the upstream and downstream is same. Once again, I want to recall that in case of the weir, we assume that there are no friction losses, or you can say that the small friction losses are ignored in this case. That's why we say that the depth of the flow come back to its original state. Now, if you further increase the height of the hump, you can see that here the height of the hump is very small. Here it is increased, and it is increased here again in this case. And you can see that in case number 3, this is the height of the hump, and you can see that when water will approach the weir, there will be an appreciable decrease in the depth of the flow, after which the flow will not come back to its original state. The flow has been converted from subcritical to the supercritical state. At the upstream side of the weir, you can see that we have the high depth of the flow. So this is a subcritical state, and obviously on a mild slope, we always have the subcritical state of the flow. And at the downstream side, we have this supercritical state of the flow, because you can see that the depth of the flow has been reduced. So there will be a critical depth of the flow on the weir. This is what we were discussing, that in case of the weir in case of weir on a channel, or across the channel, we may or we may not have the critical depth of the flow. You can see that this is the weir on a channel, this is a weir on the channel, but in both of these cases there is no critical depth over the weir. However, in this case we have the critical depth of flow over the weir. In this situation, you can see that okay, this height of the hump, or this height of the weir, is known as the critical height, and it is denoted by P critical. Why it is known as the critical height of the hump? Because it gives you the critical flow and the critical depth over the hump. Now what happens in case number D? You can see that the height of the hump is increased beyond the critical height of the hump. So what will happen when you further increase the height of the hump? There will be no change in the critical depth of the flow. The critical depth cannot be further reduced. Why? Because the critical depth is the depth of flow at which specific energy is minimum. We know this from the specific energy diagram, that at this depth of the flow we have the minimum specific energy for a given discharge. So the energy cannot be further reduced, and we can not have the further reduction in the depth of the flow. So what will happen? Instead of decreasing this depth of flow, the level of water at the upstream level will get increased, and now this is known as the damming action. Damming action means that going the situation of a dam. What is the function of the dam? The function of the dam is to store water in a reservoir at its upstream side. So if you are increasing the height of the hump, what are you going to do? You are going to increase the level of water. So if you want to have the critical depth of the flow over where, and you want to have a control section, then this height of the hump is enough. Okay, this is the enough height of the hump you have. There is no need to have this height of the hump, because in both the situations you have the critical depth of the flow. In both the situations you can have the control section. However, this will be uneconomical case, because you will it will be a cost project for you to have the height of the hump greater than this height of the hump. Okay, so it's better to have this height of the hump. If you want to have a critical flow over here, this will be economical control section, and if you increase the height of the hump, it will get uneconomical. So this was a simple discussion, and now we are going to discuss these situations in detail. So what will happen if you are going to construct a hump on a mild slope, that is a case of the subcritical flow? You can see here the same situation is shown in the single figure, that you have a mild slope, and on a mild slope you have a hump. You can see that this is a hump, or this is a weir, and you can see that this is the depth of the flow at the upstream side, which is denoted by y1. Okay, and this is the energy line, which will remain constant, because there are no friction losses in this case. In all cases of the weirs, there are no friction losses, so the energy line remains constant and straight. You can see that this is the depth of the flow y1, and what is this is the velocity head, v1 square divided by 2g. So this is the total energy at the upstream side. E1 is the total energy. So what will happen when you construct a hump? The water will approach the hump, and you can see that this is the depth of the flow, y2. Y2 is the depth of the flow, E2 is the total energy of the flow on the weir, and what is this? Delta Z. Delta Z is the height of the hump. Delta Z is the height of the hump. Okay, you can see that E2 is smaller than E1. Okay, E2 is smaller than E1 just because of this delta Z. The loss in energy is only due to the height of the hump. Greater the height of the hump, lesser will be E2. When you will increase the height of the hump, when you will increase this term delta Z, E2 will get smaller and smaller and smaller. You can see here that if you increase the height of the hump, a situation will reach when you will get this dotted depth of the flow, which is the critical depth of the flow. And at that critical depth of the flow, we will say that this is the maximum height of the hump, delta Z maximum here, and the energy will be EC, that is the critical energy, or you can say it will be the minimum specific energy. We know that at the critical flow we have the minimum specific energy at the and that's the point where we have the critical depth of the flow. Okay, remember that this is section number 1.1 at the upstream side. Here it is written, this is section number 1.1, where we have the depth of the flow y1 and energy E1, and this is over the hump. This is section number 2.2, where we have the depth of the flow y2 and energy E2. And with the increase in the height of the hump, this situation at section 2.2 will be changed, and at last it will come to YC and EC. We can explain this situation with the help of the specific energy diagram. Also, you can see that this is the specific energy diagram for the constant discharge. Here at the x-axis we have the specific energy head, and at the on the y-axis we have the depth of the flow. Okay, you can see that this is the specific energy diagram, and this is section 1.1, this is section number 2.2, the same sections which we have discussed in our above figures. Section 1.1 is at the upstream of the weir. Here you can see that this is section 1.1 at the upstream of the weir, and section 2.2 is over the weir. So these are the same sections, section 1.1 at the upstream of the weir and section 2.2 over the weir. You can see that in section 1.1, this P shows the energy at section 1.1. If you come to if you extend a line to the x-axis, you will come to know that this is E1, or simply here this is E1. Okay, this is E1 at point P, or at section 1.1, and when the water flows over the weir, its energy get reduced. This is the section 2.2, let's suppose, and at section 2.2 you can see that this point R shows that this is the depth of the flow, Y2. Y2 is the depth of the flow at section 2.2 over the weir. And what is the energy at section 2.2? If you come towards the x-axis, you will know that E2 is the energy at section 2.2. And you can see that the difference between E1 and E2 is due to delta Z. Delta Z or delta Z is the height of the hump. The difference between the two energies is only due to delta Z. Here you can also see in this figure, you can see that E1 minus E2 is equal to delta Z. So this is delta Z is the difference between the two specific energies held. Now, what happens if you further increase the height of the hump? When you will increase this height of the hump, what will happen? Section 2.2 will comes towards the downstream side, towards the downstream side in the specific energy diagram, and what will happen? It will finally comes to join this point C. When it will come at point C, then you will say that here we have the critical depth of the flow, and the specific energy will be minimum here. If you come towards the x-axis, here we have the minimum specific energy, and you can see that this is the situation where we have the maximum height of the hump. Okay, so this is the minimum specific energy, and this is the maximum height of the hump, or you can say that this is the minimum height of the hump for the critical depth of flow. In fact, you will say this is the minimum height of the hump for the critical depth of the flow. If you further increase the height of the hump, then the critical depth of the flow will remain there over the weir. So this is the minimum height of the hump for which you have the critical depth of the flow. Below this height, you don't have any critical depth, and above this height, you always have the critical depth of the flow. Now the question arises that what happens if you further increase the height of the hump? From this figure, you can see that if we further increase the height of the hump, then there is no situation for the depth of the flow, because this is the critical depth of the flow, and it can't go here because there is no specific energy diagram here. There is no physical situation actually. So what will happen? Instead of this point 2, section 2.2, which is already at this point C, what will happen if you further increase this height of the hump? Section 2.2 will remain constant over here, but section 1.1 will start moving towards the upstream side. And that will be the damming action. That will be the situation of the damming action. That will be the case which I have already shown you in your Franzini book, that if you further increase the height of the hump, then what will happen? There will be a rise of water level at the upstream side. Here is another graph. You can see that this is a plot between the depth of the flow and the height of the hump. On the x-axis we have taken the height of the hump, and on the y-axis we have taken the depth of the flow. You can see that initially this is the depth of the flow. Okay, this is any depth of the flow. This is the initial situation. And what happens when you installed a weir, or when you installed a hump on the channel? What will happen when water will approach the hump? Then over the hump, its depth of the flow will start decreasing. You are increasing the height of the hump, and you can see that the depth of the flow is decreasing. Here, this is the increased height of the hump, and the depth of the flow over the hump is decreasing. But here you can see that the depth of the flow at the upstream side, that is y1, is constant until it reaches the critical depth of the flow. At the critical depth of the flow, you can see that this is the situation of y2. This y2 is actually now yc, and the depth of the flow is also constant till yc. But if you further increase the depth of the flow, now you can if you further increase the height of the hump, you can see that we are further increasing the height of the hump. Now you will see that now critical depth is constant. Okay, there will be no change in the critical depth of the flow. It will get constant, and what will happen? The depth of flow at the upstream will start increasing. That is known as the damming action. Okay, so remember that till yc, y1 is constant and y2 is decreasing. Once you get the value of yc, then yc becomes constant and y1 starts increasing if you are increasing the height of the hump. So this is what we will do in our next class. Inshallah, we will design the weir for the critical situation. We will see that what can be the minimum height of the hump for which we have the critical depth of the flow, so we don't have any damming action also. And we usually avoid the damming action because you know that there should be a proper increase in the depth of the flow, which is allowed by the banks of the canal also. Otherwise, what will happen? The water will start to overflow the banks of the canal. That is not an acceptable situation. Okay, this is the situation for the subcritical flow. And for the subcritical flow, what will happen? First of all, we will look into the actual physical situation. Okay. You can see in this figure that we have a steep slope. Okay, remember, whenever we talk about the subcritical flow, it is always on a mild slope, and whenever we talk about the whenever we talk about the supercritical flow, it is on the steep slope. In the first case, we discussed that what will happen when a hump is installed on a mild slope, and now we are going to discuss that what will happen if the hump is installed on the steep slope. Okay, you can see that this is the steep slope over which we have a weir, and you can see that the critical depth line is above the normal depth line. In other words, yc is greater than y naught because this is a supercritical state. And what will happen once again? The fast moving water, or you can say the flow having high velocity, is coming towards the weir, and here since it gets an obstruction or a sudden break in its velocity, so what will happen? There will be a hydraulic jump and the depth of the flow will be increased. So this is an important situation, that the depth of the flow will be increased. Okay, in case of the subcritical flow, we discussed that when there is a flow, then in a channel, then over a weir, the depth of the flow will get decreased. But in a supercritical state, we say that the depth of the flow get increased. And here you can see that this was the depth of the flow in a channel, and now this is the depth of the flow over weir. So again, if we look into this specific energy diagram, you can see now we will assume that the hump is installed on the steep slope, and again we will assume that section 1 is at the upstream side and section 2 is on the rear. And now we have come to know that when a
मैम,
water G
एक्सक्यूज मी मैम।
G
मैम, आप अगर उर्दू में पढ़ाए तो ज्यादा बेहतर होगा, कोई फॉरेनर नहीं है हमारे क्लास में।
बच्चे बात ये है ना कि ये जो होते हैं ना, ये मैंने रिकॉर्डिंग पे लगाया हुआ है आपकी क्लास में। तो ये जो रिकॉर्डिंग है ना, ये फिर मैंने शेयर करनी होती है सेक्शन डी के साथ भी, वहां पे फॉरेनर्स हैं, उनको फिर प्रॉब्लम होगी।
ओके मैम। मैम लेकिन फिर थोड़ा आहिस्ता आहिस्ता पढ़ाया करें, ग्राफ बहुत कम्प्लेक्स है तो समझ नहीं आ रही इतनी जल्दी
ठीक है,
से।
ठीक है, ओके ओके ओके, दैट्स फाइन।
थैंक यू मैम।
ओके, अच्छा जी। Okay, in case of the steep slope, now if we look at the same figure, we come to know this was the figure of the mild slope, where we have section 1 at the upstream side and section 2 over the hump. In case of the steep slope, we will again have the same situation. We will assume that section 1 is on the upstream side and section 2 is over the weir. However, the situation will be different. In case of the mild slope, here we have the greater depth of the flow that is getting decreased over the weir. But in case of the steep slope, the situation will be different. We have the smaller depth of the flow that will get increased over the weir. Okay, so remember that situation, section 1 is at the upstream side and section 2 is at the downstream side in case of the steep slope also. Since in case of the steep slope we have the supercritical state, so when we will come to the specific energy diagram, we will look at the lower limb of the curve. Why? Because we know that the upper limb of the curve is for the subcritical state and the lower limb of the curve is for the supercritical state. When we were discussing the hump in case of subcritical state, we discussed the upper limb, and now since we are discussing the hump on a steep slope or hump in case of the supercritical state, therefore we are going to discuss the lower limb of the curve. Okay, again you can see that here we have we will look at the lower limb of the curve, and we can see that this is section 1 okay, this is section 1 and you can see that here we have the depth of the flow. अगर आप यहाँ से depth of the flow को देखें, here we have the depth of the flow y1. And what will happen when it goes to section 2 section 2 is over the weir. When the flow will goes to section 2 its depth of the flow will get increased. After hydraulic jump, the depth will get increased, and you can see now if you extend a line towards y-axis, you will come to know that the depth of the flow at section 2 is higher than the depth of the flow at section 1. Okay, and what's the difference between the two energies? Here we have energy E1 and here we have energy E2. And what is the difference between the two energies? The difference between the two energies is delta Z, that is the height of the hump. Now from this figure, if you can see that if we increase the height of the hump, what will happen? If you increase this height of the hump, section 2 will start moving towards the upper side, okay, until it comes to this point. When section 2 or you can say when this point R dash will join the point C, at that point we will have the critical depth of the flow and the critical or the minimum specific energy, okay, and the height of the hump will be delta Z M. This will be the minimum height of the hump for which we have the critical depth over the weir, and there is no need to further increase the height of the hump, because what will happen, there will be no change in the critical depth of the flow. From the specific energy diagram you can see that there can be no further reduction in the depth of the flow because it has already gone to YC. So what will happen if you further increase the height of the hump, then there will be no change in YC, but what will happen? This depth of the flow will get decreased at section 1.1. Okay, at section 1.1 the depth of the flow will get decreased. You can see that this point P dash will further come towards at the downstream side. Here in case of the supercritical state, we say that when this point R will join the point C, then what will happen if you further increase the height of the hump? This point P will start moving towards the upper side. When point P will move towards the upper side, you can see that the depth of the flow will increase. In this case, we will say that when point R dash join the point C, then there will be no further reduction in the depth of the flow over the hump. And what will happen if you further increase the height of the hump? Instead of point R dash, point P dash will start moving towards the lower side, and when point P dash will move towards the lower side, you will come to know that the depth of the flow is decreasing. Okay, so in the case of the subcritical flow, the depth of the flow at the upstream will get increased if you increase the height of the hump beyond the critical limit. And in the case of the supercritical state, the depth of the flow at the upstream side or at section 1.1 will get decreased when you further increase the height of the hump. And this situation can be clear from this curve, that is between the depth of the flow and the height of the hump. Oh, sorry, this is for the subcritical state. Yes, this is for the supercritical state. You can see that if we draw a graph between the depth of the flow and the height of the hump, here we have depth of the flow on the y-axis and the height of the hump on the x-axis. You can see that initially this was the depth of the flow. Okay, I'm talking about the steep slope having hump. When there is no hump, then this is the depth of the flow. When you install hump across the channel, what will happen? You can see that the depth of the flow at the upstream, that is y1, it will remain constant, but depth 2 will get increased with increasing height of the hump. And how the depth of the flow get increased? It increased due to the hydraulic jump. Okay, so you can see that on the x-axis we are increasing the height of the hump, and here you can see that the depth of the flow is increasing, and it will increase till this situation where we will get the critical depth of the flow. This is the critical depth of the flow. This YC is with this indication, okay, with this line. This shows you that here we have the critical depth of the flow. And beyond the critical depth of the flow, if you further increase the height of the hump, what will happen? You can see that now this YC remains constant. That is, the depth of the flow over the weir remains constant. And what will happen? The depth of the flow at the upstream will start to decrease. Okay, you can see that these two cases are just opposite to each other. Subcritical and supercritical have just opposite situations. In case of the subcritical state, when we have a hump on the channel, you can see that the level of water at the upstream is higher, and when it goes to the weir, then it get decreases. While in case of the supercritical flow, the depth of flow at the upstream is lower, and when it approaches the weir, then the depth of the flow increases over the weir. Okay, so these are just the opposite situations. Okay, what happens in both the cases when we increase the height of the hump beyond the critical height of the hump? In case of the subcritical flow, if we increase the height of the hump beyond the critical height of the hump, then there will be a damming action and the level of water at the upstream will get higher. While in case of the supercritical flow, the level of water at the upstream will be further reduced. So this was the discussion about the hump on the channel in on a mild slope and on a steep slope. Now it is easy to understand the second transition, that is when you provide a contraction in the width of a channel, what will happen. Similarly, we will discuss it for the subcritical flow and we will discuss it for the supercritical flow as well. Okay, this is the first case, that is for the subcritical flow, or you can say that when we provide a channel contraction in case of a mild slope. Now, now imagine that there is a channel having mild slope and the actual width of the channel is B1. Here you provide the contraction and the channel has been contracted to the width B2. Since B2 is smaller than B1, okay, first look at this side view of the channel. Here you can see that in a channel, the depth of the flow is Y1, and when it comes to the contracted section, the depth of the flow will be decreased by Y2. Okay, however, the total energy will remain constant. Again, we are ignoring the friction losses, so we will say that the energy line will remain constant. If you further contract the channel width, what will happen? This y will get decrease and decrease until it reaches at the level where you have the critical depth of the flow. Okay, we have the same situation as in case of the weir. Weir में भी हमने यही कहा था कि when flow approaches a weir, what will happen? The flow over the weir will get decrease and decrease and decrease until it reaches the critical depth of the flow. Okay, here we will again say that when you are contracting the width of the channel, then what will happen? The depth of the flow in the contraction will get decrease and decrease until it reaches the critical depth of the flow, and that will be the situation where we have the critical flow in the contracted section of the channel. Okay, but there's only one difference. In case of the hump, we say that the discharge in a channel is equal to discharge over the hump. Why? Because the hump is constructed across the width of the channel, across the whole width of the channel, from one bank of channel to the other bank of the channel. So we say that the whole width of the channel is equal to whole length of the weir. Okay, that's why there is no difference in discharge. The discharge in a channel is equal to discharge over the weir. However, in case of this contracted section of the channel, you can see that the width has been reduced, or you can say that the area of the flow has been reduced. So what will happen? The discharge will get maximum here. Okay, here the discharge is smaller in a channel, but when it will come in the contracted section, the area will get smaller, so the velocity will get higher and the discharge will be increased. This is similar to that of the dia of the pipe. Greater the dia, smaller the discharge, and smaller the dia, greater the discharge or greater the velocity. So this is the same concept, that when you decrease the area of the flow, then the discharge get increases. So what will happen when you draw the specific energy diagram for this channel, then what will you do is, we know that the specific energy diagram is for the constant discharge. Since in this case the discharge is not constant, therefore you will get different specific energy curves. For example, here the discharge is different from the discharge in this contracted section. So for this section, that is for the channel, you will have a different specific energy diagram, and for this contracted section you will have the different specific energy diagram. The specific energy diagram depends upon the discharge. When discharge will change, then the specific energy diagram will also change. You can see that these are the specific energy diagram for the contracted section. Once again, this is the on y-axis. We know that for specific energy diagram on y-axis we have the depth of the flow, and on the x-axis we have the specific energy. Okay, now look at this first curve. This first curve is for a discharge Q1. And what is this small q? This is the unit discharge. Unit discharge is equal to discharge per unit width of the flow. Okay. So this is the unit discharge, and you can see this is for the, this specific energy diagram is for the discharge in a channel. Okay, at section 1.1 you can see. Okay, you can see that in a channel we have a section 1.1 where energy is E1 and depth of the flow is Y1. You can see this is section 1.1, and in the contracted section we have a section 2.2 where the depth of the flow is Y2. Okay, this first specific energy diagram is for the discharge in a channel. This specific energy diagram is for the discharge in a channel, and this second specific energy diagram is for the discharge in a contracted section. Okay, now you can see that this is section point P shows that this is section 1.1 in a channel. Okay, and this is the point. Yes, this is section 1.1 in a channel, and you can see that this section 1.1 touch the first curve here where you have this depth of the flow, that is Y1. So what will happen when you will provide a contraction in a channel? When you will provide a contraction in a channel, then you will get this second specific energy diagram where you can see Q2 is greater than Q1. Why? Because discharge in a contracted section is greater than the discharge in a channel. So you will get this specific energy diagram, and you can see that for this specific energy diagram, now we have this depth of the flow, that is Y2. And this is what we are saying. You can see that Y1 is greater than Y2. Here in this figure, you can also see that Y1 is greater than Y2, which shows you that when water comes in the contracted section, the depth of the flow will get decreased, which is also shown in the specific energy diagram. You can see that in the second specific energy diagram. Now this is the situation where we have the Y2, that is the depth of the flow in the contracted section. You can see that E1 is the energy in the E1 is the specific energy in a channel. And what will happen if you increase the contraction of the channel? When you will further reduce the contraction of the channel, then you will draw another specific energy diagram. Here you can see that with the reduction in the width of the channel, the depth of the flow will get reduced in the contracted section until it reaches the critical depth of the flow. And this is shown by the dotted specific energy diagram. Here you can see that here we have written that this is the maximum discharge, okay, for the contracted section where you will get the critical depth of the flow. You can see that this is the critical depth of the flow for the contracted section of the channel. Okay, and what will happen if you will further reduce the width of the channel by increasing the contraction? Then what will happen? Again, we will have the same situation. In case of the hump, we say that when the height of the hump goes beyond the critical hump height, then there is damming action, that is the level of water at the upstream side increases. Similarly, in case of the contracted channel, we say that if we further provide the contraction beyond the minimum value, then what will happen? There will be a damming action at the upstream side of the channel. That is, what will happen? This y1 will start increasing. Okay, yc will not get further reduced, but what will happen? This y1 will get start increasing. The depth of the water will get increasing. However, when this depth of the flow will get increased, the value of yc will also change. The depth of the flow will be yc, but its value will be changed. Why its value will be changed? Because in this case the discharge is not constant, and we know that the value of yc depends upon the discharge. We already developed a relationship for the rectangular channel, that square of q is equal to g into cube of yc. That is, there is a relationship between a unit discharge and the depth of the flow. If you increase or decrease the discharge, then the critical depth will also change. In case of the hump, since discharge is constant, therefore critical depth of the flow is also constant. In this case, if you further reduce the contraction, then what will, if you further provide the contraction in a channel, then what will happen? There will be a further change in the discharge of the channel, and this depth of the flow will be changed. The critical depth of the flow will be changed, but that change depth of the flow will be also a critical depth of the flow. ठीक है, आपको समझ आ रही है? इंशाल्लाह हम न्यूमेरिकल प्रॉब्लम्स भी करेंगे. फॉर एग्जांपल, the depth of the flow is, let's suppose, 1 meter. Okay, and what will happen if you further reduce the width of the channel? This depth of the flow will increase, and the critical depth will also increase. Critical depth was 1 meter, and now let's suppose the new critical depth of the flow will be 1.2 meter. Okay, the critical depth of the flow will also increase, but will remain critical depth. Depth change होगा, लेकिन वो critical depth ही रहेगा आपके पास. ठीक है, तो कहने का मकसद ये हुआ कि सिचुएशन आपके पास वही है कि अगर आपने, इफ यू वांट टू हैव अ कंट्रोल सेक्शन इन द कॉन्ट्रैक्टेड सेक्शन, if you want to have a critical situation in the contracted section, then you must provide the maximum width, maximum contracted section, which gives you the critical depth of the flow. उससे ज्यादा contraction provide करने की जरूरत ही नहीं है ना, क्योंकि you are going to increase the contraction, and what is going on? You are again getting the critical depth, the critical depth. Then why are you going on uneconomical side? ठीक है, तो ये भी इंशाल्लाह ताला we will solve the numerical problems, and we will analyze the channel for the contracted section in our next class, where we will say that what can be the maximum contraction of the channel where we can have the critical depth of the flow. Here you can see that this is a kind of little bit complicated figure, but once you come to know it, it will get easy. On y-axis, we have the depths of the flow. Y1, Y2, and specific energy all are shown on the y-axis, and on the x-axis, we have the ratio of the two widths of the channel, B2 divided by B1. B1 is the width of the channel, and B2 is the width of the contracted section of the channel. So B2 by B1. Okay, what will happen? You can see that this is the initial depth of the flow. Okay, this is the Y1. Y1 is the initial depth of the flow, and E1 is the initial energy of the flow. So what will happen now if you are reducing the ratio, or you can say if you are increasing the contraction of the channel, you will go towards the left side, and you can see that the depth y1 is in a channel. The depth of the flow y1 will remain constant, and the depth of the channel in the depth of the flow in a contracted section is decreasing. It will get decreased until it reach at this point where you have the critical depth of the flow. Okay, here you have the critical depth of the flow. Now what will happen once you get the critical depth of the flow, your design should be stopped here. But if you don't stop here and you further increase the contraction of the channel, then what will happen? Then there will be a damming action. The depth of the flow on the upstream side will get increased. You can see that Y1 is increasing now. Okay, the depth of the flow Y1 will start to increase here, and here in the contracted section Y2 will again starts to increase, and it will get a point where again you have the critical depth of the flow. Okay, here you have the critical depth of the flow. Again, here you have the critical depth of the flow. So you should stop here. In this situation, if you want to have a critical flow, then you should stop at this critical depth of the flow. However, if you don't get stop and if you further increase the contraction, this Y1 will further get increased and you will get different values for the critical depth of the flow. Remember that critical depth of the flow depends upon the discharge. When discharge will change, then the value of the critical depth of the flow will also change. If the you can see here, let's suppose initially the critical depth of the flow was, let's suppose, 0.5 meter, and now you can see that the new critical depth of the flow is, let's suppose, 0.7 meter. But in case of the weir, this is not the case. If the critical depth of the flow is, let's suppose, 0.6 meter, it will remain constant, 0.6 meter. Okay. And now we have the last case of the supercritical flow. In the same situation, that will be opposite of the subcritical flow. We will say that, let's suppose, okay, if we assume the same figure and we assume that now it is on the steep slope, now you can make the figure by yourself. And what will happen if this is a steep slope and you provide a contraction? If this is a steep slope in a channel and if you provide a contraction in a channel, then what will happen? We know that the velocity of flow is higher on a steep slope. So when it will comes to the contracted section, again there will be a hydraulic jump, and after hydraulic jump, the depth of the flow will be increased in the contracted section. So this figure will be opposite. Here you will draw the lower depth of the flow for the subcritical state, then you will draw a hydraulic jump, and after hydraulic jump you will show that the depth of the flow has been increased in the contracted section of the channel. Okay, just make a figure opposite to that of figure. Here the depth of the flow is higher, which get decreases in the contracted section, but in a steep slope you will show that there is a low depth of the flow, and after hydraulic jump it gets higher in the contracted section of the channel. So you will say that in case of the steep slope, when you increases the contraction, then what happens? The depth of the flow get increased and increased until it reaches the critical depth of the flow. Okay, and again you will say that if you will further increase the contraction of the channel, then what will happen? The water at the upstream will get more less. The depth of the flow will get more less, and the discharge will be changed in the contracted section also, and you will get a new critical discharge. This is just opposite to that of the subcritical state. Here you can see that if we look at the supercritical state, then we will have to look at the lower limb of the curve, and you can see that this is the first section, section 1-1, where we have the depth of flow in a channel. Okay, you can see that initially this initial curve is for discharge Q1, that is the discharge in a channel, where we have this section 1-1, and you can see that at this section 1-1, this is the depth of the flow in a channel. This may be Y1. Let's suppose this is Y1. Now you provide the contracted section where the discharge get increased, and you get this second specific energy curve where Q2 is greater than Q1. That is, the discharge in a contracted section is greater than the discharge in a channel, and you comes to this point. at this point, you comes at this point R, and you can see that at point R the depth of the flow is greater than the depth of the flow at point P. This shows you that when the water flows from the channel into the contracted section, the depth of the flow will get increased. If you further increase the contraction of the channel, then what will happen? This point R will move towards point C in this dotted curve. It will move towards point C where you have the critical depth of the flow. Okay, once you get the critical depth of the flow, then what will happen if you further increase the contraction of the channel? You can see that the this point P will move downward. You can see that let's suppose we have got this curve where we have a very high discharge. Okay, if you get this curve, you can see that this is the new critical depth of the flow for the contracted section. Okay, and this is the specific energy. So you can see that the value for the critical depth of the flow is also getting changed in case when the discharge is changing. And this is the last figure which is plotted between the depth of the flow and the ratio of B2 divided by 1. You can see that on y-axis we have the depth of the flow, on the x-axis we have the ratio of the widths, and you can see initially we have this depth of the flow. Initially we have this depth of the flow, and you can see that depth y1 is constant, is almost constant when y2 is getting increased in the contracted section. Okay, you can see that this is depth y2. This is the depth of the flow in the contracted section, and it gets increased after the hydraulic jump. The depth y2 is getting increased and increased until it reaches the critical depth of the flow. You can see here we have the critical depth of the flow, and if you further provide the contraction in a channel, what will happen? Y1 at the upstream side will start to get decreased, and y2 will start to get increased, and you will get a new value for the critical depth of the flow. ओके, आप करेंगे क्या? आप जस्ट किसी एक केस को अपने ज़हन में रखें. फॉर एग्जांपल, आप अगर हम को डिस्कस कर रहे हैं तो आप सब क्रिटिकल को सिर्फ अपने माइंड में रखें, सुपर क्रिटिकल बिल्कुल उसके ऑपोजिट चलेगा. इसी तरह अगर आपने इस ट्रांजिशन को डिस्कस करना है कि व्हाट विल बी हैपन व्हेन यू प्रोवाइड कंस्ट्रक्शन इन अ चैनल, just remember that what will happen in case of the subcritical state, and you must know that the case of supercritical flow is just the opposite of the subcritical state. ठीक है, तो किसी एक केस को, किसी एक फिगर को ज़हन में रखें और दूसरा जो होगा वो उसके ऑपोजिट चलेगा. एंड ऑलवेज कीप इन माइंड दीज थिंग्स बाय द कंपैरिजन. हमेशा कंपैरिजन कर करके चलें. What is going on in the subcritical state and what is going on in the supercritical state. Okay, so this was all about our today's class. आप इसको एक दफा जरूर देख लें before our next class, because in our next class we will develop the general equations for the hump and for the contraction in a channel, and we will solve numerical problems on the basis of that equations and on the basis of the concept discussed in our today's class. ठीक है, तो आप इनको अच्छी तरह से पढ़ लें, and if you get any problem then we can discuss it in our next class.